All right, in this video, we're going to review the first half of Unit 8, all the convergence and divergence of infinite series. So this first question says, which of the following series converges? So just looking at all the answer choices, it looks like they are all alternating. So I'm going to be using the alternating series test. So the alternating series test says if the series is alternating, then the series converges if two things happen. If the limit as n goes to infinity of the non-alternating part, that limit has to be 0. And then this first one, the limit of the non-alternating part, that limit as n goes to infinity is 1/3. So that one diverges by the, I guess you can say alternating series test, or I can even say the nth-term test. Looking at this one, I might have to rewrite this a little bit, 2n to the 1/2. At this point, I realize that the non-alternating part, that limit is not 0. So neither one of those is the answer. Part C, this one has potential. Looking at this one real fast, the limit of the non-alternating part, that would be -1, which is not 0, so it's not that one. So it is a, I'm going to double check and just make sure. The limit as n goes to infinity of 2 to the n 1/2 over n. That limit is 0. The bigger degree on the n part is on the bottom, so of course that one's going to blow up faster. And then also, it has to be non-increasing. This function right here, this part right here, this non-alternating part, we would call that just a of n, that has to be non-increasing. So just to like confirm that, I'm going to say this is going to be f, I'll say f of x is equal to 2x to the 1/2 over x. And we have a couple ways to say it's non-increasing. We could look at a ratio of the n+1 term and the nth term, or an algebraic difference. I think one that I've kind of liked lately is the derivative test. So if the derivative is less than or equal to 0, then it's non-increasing. So I'm going to take the derivative of this. Actually, I'm going to say this is equal to 2 over x to the 1/2, kind of clean that up a little bit, just subtract the exponents. And then I'll do, this would be equal to 2x to the -1/2. The derivative of that would be -1/2 times 2, which is -1. Subtract 1 from the exponent, it's a little power rule. This would be -1 over x to the square root of x cubed. So that will be positive, or this will always be negative, which means it is non-increasing. So the answer is C. All right. The next one, it says, what is the value of this infinite series? The only series we really know we can find the value of is those geometric series. So anytime it says find the value or find the exact sum of the series, that's kind of like a clue that this is geometric. And I know geometric series converge to the first term over 1 minus r. So I've got to look at, this is equal to, if I would just rewrite this, I would rewrite the top as 2 times 2 to the n over 7 to the n, which could be rewritten as 2 times 2 over 7 to the power of n. So now this is the r number. If that r number is less than 1, then that geometric series converges. If it's greater than or equal to 1, it would diverge. But this one converges, and it converges to the first term. So I gotta be real careful. This would be different if n started at 2 or at 3 or at 4. It matters what the first term is. So it's the first term, plug in 1. So it would be, I could just plug in 1 here, I could plug in 1 here. So it would be 2 times 2/7. So that would be 4/7. 4/7 is the first term, divided by 1 minus the r number, which is 2/7. So if it was free response, I could leave it. I'm going to clean this up just to practice. 4/7, okay, 1 minus 2/7 is 5/7. This would be equal to 4/7 times 7/5. The 7's cancel, 4/5. That would be the exact value of that series, which is only possible because it's geometric. All right, which of the following series can be used with the limit comparison test to determine whether the series converges or diverges, this series? So looking at this one, when I'm trying to pick out a limit or a series to compare with the limit comparison test, I'm going to look at the big terms. And looking at the big terms, I can see that that's pretty much going to be just 2 to the power n over 3 to the n. The little stuff doesn't matter. So look at the most powerful terms. Then that can be rewritten as a geometric series 2 over 3 to the n. So that one would be C. Yeah, pretty sure about that one. I guess I should make sure it actually works. So that's just what I would pick. Now I need to make sure I get a positive finite number, right? So the limit comparison test says these two series that you're comparing, if you take the limit of one of them over the other, doesn't matter which one over which one, I'm gonna say it's the original divided by this. And if I'm dividing that, I'm gonna multiply by the reciprocal, which would be 3n over 2 to the n. If that is equal to a positive finite number, then the series act the same. So if I don't get a positive number, so I get like 0, or I don't get a finite number like I get infinity, then limit comparison test doesn't work. So let's just make sure we do get this. Those 2 to the n's clearly cancel. If I look at the limit as n goes to infinity of 3 to the n over 3 to the n minus n squared, that limit is 1. And 1 is positive and finite, so it works. They act the same. So since I know this geometric series converges, so does this one. All right, this one's calculator active. Not a huge fan of this question, but it's on here. Okay, it says find the sequence of the partial sums. So find S1, S2, S3, S4, S5. Okay, S1 is just equal to the first term of the sequence added together. So since my first counting number is 1, I plug in 1. I get 3 over 2 to the 0, which is just 1, so this is just 3. S2 stands for the partial sums with two terms of the sequence. So it's 3 plus the next term in the sequence. I'll get by plugging in 2. Plug in 2 for the n. So that would be what? 3 over 2 minus 1 is just 1, so 2. I can make this 6 over 2 plus 3 over 2, so that's 9 over 2. The third partial sum would be 9 over 2, which is the second partial sum, plus the next term in the sequence. So S3 would be given by doing S2 plus A sub 3. So S sub 2 was 9 over 2, plus the next term in the sequence, which is going to be 3 over 2 squared. So this is going to be equal, get a common denominator of 4, so 18 fourths plus 3 fourths, so 21 fourths. I get S4 by taking S3, partial sum with 3 terms, and adding the next term of the sequence, so the fourth term of the sequence, which would be 3 over 2 times 2 times 2, which is 8. Common denominators, 45 over 8. It said find S5. S5 is S sub 4 plus A sub 5. So the fourth partial sum plus the next term of the sequence would be what, the fifth term. So 2 to the fourth. 2 to the fourth would be 16. Common denominator would be 90 over 16 plus 3 over 16. So S sub 5 would be 93 over 16. All right, just getting kind of familiar with what that S sub 1, S sub 2, S sub 3, S sub 5 means, partial sums. Okay, that's it for that one. All right, number 5, verify that the infinite series blank, that thing, diverges using the Nth-term test for divergence. Show the value of the limit. All right, so the Nth-term test says if the limit of the terms of the sequence is not approaching 0, we know that series diverges, and it's super easy. So I'm going to just talk about the limit here for a second. So that's the sequence. Rewrite that bottom one, 3 to the n plus 1. I would rewrite this as 3 to the n times 3 squared. So that would be equal to basically 9 times 3 to the n. So this limit would be 1/9 which is not 0, so it diverges. So the Nth-term test only works to prove divergence. If you get the limit is equal to 0, it could still converge, it could still diverge, we don't know. All right, which of the following series converge? All right, one of these questions, converge. Okay, I see, just kind of talking through what I'm thinking. If I see factorial and exponential, I think ratio test. So probably ratio test. And then this last one, I would say this is n times n to the 1/2. Add those exponents into the 3/2. So this one converges because it's a p-series. P-series converge if this p number, the exponent, is bigger than 1. If it's equal to 1, then it's the harmonic, it diverges. Less than 1, it diverges. So which ones converge? It's not A, it's not B, because those don't include 3. So we're going to test all of them, just to be sure, even if I get B or get C, whatever. All right, so I am going to do ratio test. The ratio test looks at the limit as n goes to infinity of the a sub n plus 1 term over the nth term. So this represents the next term if a sub n is the current term. So what this is saying, if this limit is less than 1, that series converges. And I want you to think for a second. I want you to realize that the ratio test is basically like the geometric series. Okay, a geometric series converges if this R number is less than 1. Using the ratio test, it converges if that ratio is less than 1. That ratio is defined by all the different, the term divided by the one before it. So if I had a geometric series where R is 1/2, it could start out as 10, then 5, then 5/2. I should have picked an easier one, 5/4. Each time they're getting cut in half. So the ratio, let me do another one. If I did 12, 6, 3, 1.5, the ratio of a term divided by the one before it, the n plus 1 term and the nth term. That one here is 1/2, so it's less than 1. So if you have a ratio, it's not exactly geometric, but if the next term divided by the one before it is approaching some value less than 1, that's basically your R number. If that ratio is less than 1, then they converge. It doesn't have to be exactly geometric, but it should be close. They almost act the same. So the ratio test is basically the same. Does it act like a geometric series? Because we know about geometric series. All right, all that yapping. That's what the review is for, just extra yapping. So I'm going to say the limit as n goes to infinity of the n plus 1 term, and this is in absolute value, it'll be 3 to the n plus 1 over n plus 1 factorial time, or divided by the nth term, or basically multiplying by the reciprocal of the nth term. This is a review, we've done this before. Now I gotta see, this is equal to the limit as n goes to infinity. Do some rewriting. So at this point, I realize 3 to the n's cancel, n factorials cancel, and now I have this is equal to the limit as n goes to infinity of 3 over n plus 1. Okay, that ratio, or that limit is equal to 0, right? And 0 is less than 1. Therefore, this series converges by the ratio test. Now I'm going to do, and we know the answer is D now, but I'm going to also just look at this one. So at infinity, 8 over n is more powerful than the n. So I could maybe compare this with 1 over 8 to the n, which is 1 over 8 to the power of n. That converges, right? This is a converging geometric series. This basically acts like a geometric series, but with that n, it's not technically geometric, but it's close. So if I did direct, earlier I did ratio test because I like ratio test better. But this one, if I did direct comparison test, can I compare 1 over 8 to the n and n over 8 to the n? So this one's bigger, right? If the smaller one converges, we can't say the bigger one converges. So direct comparison test doesn't really work here. Direct comparison test doesn't work a lot for me. I can't ever seem to get direct comparison test to work. Ratio test, on the other hand, love that ratio test. It's n plus 1 over 8 to the n plus 1 times 8 to the n over n. The limit as n goes to infinity, rewrite 8 to the n times 8, 8n over n. So at this point, I realize that those 8 to the n's cancel, and this is equal to the limit as n goes to infinity of n plus 1 over 8n, which is equal to 1/8, which is less than 1, therefore it converges. So that ratio is 1/8. That's basically the R number for the, if it was like a geometric series, right? So that's how the ratio test kind of looks like the geometric series. All right, number 7. I'm already getting tired. Number 7. For what values of x is the series conditionally convergent? All right, so that whole idea behind conditional convergent and absolute convergent is the idea behind an alternating series where if I've got some alternating series like this one, this is the famous one, this is alternating harmonic, it converges conditionally. So it's absolutely convergent if the absolute value of this, so the absolute value just takes away the alternating part. If that was to converge, it converges absolutely. Means it doesn't need the alternating part to converge. But we know that one doesn't converge absolutely. This one converges conditionally. It needs the condition that it alternates in order for it to converge. So what is this one? I want to see where is this conditionally convergent. I could kind of guess some numbers, but it's just going to be kind of hard. Conditionally convergent when this is just exactly, when this is -1, right? If this was -1 to the n, that makes it alternate and to be conditionally convergent. So pretend we don't know that. We're going to say the limit as n goes to infinity, we're going to use that ratio test, of the n plus 1 term divided by the nth term, or multiplied by the reciprocal of the nth term. We want to force that to be less than 1. Because if that in absolute value converges, this converges absolutely. So if I find the range where it converges absolutely, then that endpoint where like it kind of switches over, I'll show you in a second, could be where it could be conditionally convergent. So this is when we rewrite limit as n goes to infinity, x plus 2 to the n times x plus 2 over n plus 1. I'm going to force that to be less than 1. That'll make it converge. At this point, that cancels, that cancels. I'm going to rewrite this limit as n times x plus 2 over n plus 1. So this part right here, the limit of n over n plus 1, if that wasn't there, so just look at the highlighted part right now. What's the limit as n goes to infinity of n over n plus 1? That's just 1, right? So this part is just 1, so I'm just left with the absolute value of x plus 2 has to be less than 1. Okay, so to get rid of the absolute value bars, subtract 2. So this interval right here, so any number for x strictly less than -1 but greater than -3, those are the points where it's absolutely convergent. Absolutely convergent. And you could test some numbers and pick a number like 0, plug in 0 right here. I've got, 0's not in between, that's embarrassing. Plug in, okay, if I plugged in 0, that's still helpful. 0 plus 2 to the n would be 2 to the n over n. That diverges by the nth-term test. So any number outside this region, that series is going to diverge for those numbers of x. For the numbers in between, they converge absolutely, like -2. That's going to be almost 2. So -2 plus 2 would be 0. 0 to the n power is 0. 0 over n is 0. That's adding 0 plus 0 plus 0 plus 0, which converges obviously. If I picked a smaller number, it would make a decimal, it would still work. So where it could converge conditionally is right where it's equal to -3, where it's equal to -1. That's like the crossover. So in between, absolutely convergent. Outside those numbers, divergent, no questions. On the edge, it's either where it could converge conditionally or converge absolutely. So I plug in -3 here. -3 plus 2 is -1. And now I realize that's an alternating harmonic that converges, but it converges conditionally. If I plug in -1, -1 plus 2 is 1, 1 to the n over n. This is just 1 over n. That series diverges altogether. So I could do a little extra work. -3 less than or equal to x less than -1. Those are the values where the series converges, but it converges conditionally when when x is -3. Converges absolutely all in between. All right, use the integral test. Some of y'all are thinking, nope, not going to do it. Just going to skip it. Use the integral test to determine the convergence or divergence of this series. Oh boy. Well, this looks fun. Before we get into actually integrating, let's just remind ourselves, what are the conditions for integral tests? They usually don't have you prove the conditions, just state the conditions. The conditions to use the integral test is, I would say, let f of x be equal to e to the 1 over x squared. Just replace the n's with x's. And then you treat it like a function. That function has to be f of x is positive. It's positive. It has to be continuous. It's continuous for n starting at 1 and greater. It's not continuous if x is 0, but it's not a problem. It's continuous for n greater than or equal to 1. And then we're just going to say it with confidence that it is decreasing for n greater than or equal to 1. So on an FRQ, if this came up on the real deal in May, you can just say that, and I think you'll be okay. But for this, because we're doing extra, let's actually confirm that it's decreasing. Now, it has to be decreasing at some point. It could increase, but as long as it's decreasing at some point, we're okay with that. But usually they're going to decrease for like all of them. So I'm going to say f of x is equal to e to the 1 over x squared. Let's find f prime. Okay, the derivative. If the derivative is negative, it's decreasing. The function is decreasing. So this is a good review for quotient rule. So it's the derivative of the top. The derivative top would be e to the, and I'm going to rewrite this as e to the negative x. E to the negative x times the chain, so times -1. Derivative of the top times the bottom, x squared, minus the top, just like it is, times the derivative of the bottom, which would be 2x, all over the bottom squared. So now I got to think, what's going on with the top? This would be, if I clean this up a little bit, maybe negative e to the negative x times x squared minus e to the negative x 2e to the x, like that. This is not what I got when I did this earlier. Derivative of the top times the bottom. Oh, I rewrote and did the product rule earlier. Okay, we'll see if this works. If not, I'll show you the product rule. Let me work through this. So this is all about the top. The bottom is going to be positive. So that's the top. Can I show that the top is always negative? I feel like if I factored out a negative e to the negative x, this is always negative, right? Negative 1 over e to the x. That's going to be negative. If I factor that out, I'd be left with x squared minus 2x. Is this always going to be negative? Is x squared always greater than what I'm subtracting? For n greater than or equal to 1, yes, it will be. This would be, oh wait, what is that? would it be at 1? It'd be 1 minus 2, which is negative, and that's 1. So that will be positive, but after a certain point, 3 squared would be bigger than 6, 4 squared. Okay, so we're just gonna say yes. It just is. And if you don't like that I just kind of said that, I'm sorry. Let me see if I could do the... How did I get it so easily on the earlier? I got it. It looks so much better. The chain. It was so clear earlier. Now it's like, is it kind of, sort of, a little bit, sometimes. Oh well. We're going to say it is. I'm getting tired. We'll probably talk about something in class before the break anyway, so we'll have talked about this one. All right, so to integrate this, now I'm going to integrate from 1 to infinity. I'm going to save some time. I'm going to say this is going to be to a. I'll do the limit as a goes to infinity, so an improper integral, indefinite integral, of e to the 1 over x squared dx. I got to think, okay, this is going to be some u substitution, and it's going to be real tricky. I'm going to say u is equal to 1 over x, which is equal to x to the negative 1. That means du is equal to negative 1 x to the negative 2. So this would be rewritten as negative 1 over x squared, right? So that 1 over x squared is this right here. But the only case I need to make it negative, so I'll say this is equal to, I said the limit as a approaches infinity of a negative integral from 1 to a. Now I shouldn't do the 1 and the a. I should just keep these. This is going to be terms of u for a second. This is going to be e to the u, and I'm going to change my limits integration back in a second, du. So it's just the negative of that. Okay, find the antiderivative of e to the u. That's e to the u. So this is the limit as a approaches infinity. E to the u, but u is 1 over x. Evaluated, and this will be negative, right? Negative of this. What was it doing? 1 to a. This will be equal to the limit as a approaches infinity of negative. Okay, so plug in a, e to the 1 over a minus e to the 1 over 1, which is just e. Make that negative. This would be equal to the limit as a approaches infinity of e minus e to the 1 over a. That limit is equal to e minus 1. As a gets huge, 1 over a approaches 0, e to the 0 is 1. So that means the improper integral converges, and it converges to this. So we can say that this series converges. I don't know what it converges to, but it converges by the integral test. I'm wondering, I want to go back and just prove that some other way. I shouldn't spend more time on this. Okay, that would be, it's decreasing. Yeah, I don't know. All right, number 9. Let's see, which of the following series converge? All right, this one converges. That's a geometric series with R number less than 1. That one converges. This would be 1 over n to the 1/2 times n to the 1, which is 1 over n to the 3 over 2. That converges, converging P series. As long as that P is bigger than 1, it converges. So it's not 1 only, it's not 2 only, it's not 3 only. It's not 1, it could be D or E. So we need to do this one. And good news, this is another integral test. Now, I might try a limit comparison test with 1 over n. I know this series diverges, right? But looking at these two terms, starting at 2, notice this one can't start at 1. If n was 1, natural log of 1 is 0. There's 0 on the denominator. You can't divide by 0. Everything's wrong. This one starts at 2. So if this number, natural log of starting at 1 or starting at 2, natural log of 2 is like 0.69. So natural log of the numbers is getting bigger, multiplying by a number. So the bottom's getting bigger, so it's less. If the top one diverges, we can't say anything about the bottom one. So there's another direct comparison test, not super helpful. So this one, I am going to say we're going to need to do the integral test. So integral test, just look at this as a function. For values of n at 2 and greater, we're going to say it's positive, continuous, and we're going to say it's pretty obviously decreasing. The top is fixed, the bottom is getting bigger, so overall the fraction is getting smaller. So integral test, I'll say this is the limit as a approaches infinity, integral from 2 to a of 1 over natural, or n natural log of n, dn. So the u here is going to be probably natural log of n, because what is du? What's the derivative of the natural log of n? It's 1 over n, and that 1 over n is right there. So it'll be in the du, and it doesn't help that I write my n's like u's. So this would be the limit as a approaches infinity. And for fun, this time we could plug in, this is the natural log of 2, this is the natural log of a, but I just don't ever do that. I'm just going like blah, 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 blah. I'll fix it in a second. This would be 1 over u du. Just a second. I gotta stop this video. I'll record later.